In the previous video, we introduced the idea of an operator. And let me just remind you that what an operator is it's a function that works on functions. So an operator, or we can think of it as a machine, basically, and it takes in a function and gives out a function. So let me put here, so we have function in to the machine, and we get a function out. Now, when we deal with the function, we're thinking of things like y equals f of x. And so when we do that, this variable y, or the variable x, is what we call the independent variable. Independent variable. And the y is the dependent variable. So we only have two variables for the kinds of functions we're working with. They take in one value and they give one value out. So the value that goes in is the independent variable, the value out is the dependent variable. And when we're working with operators, we have a function in and a function out, okay? And the deal here is that both of these functions have the same independent variable. So for example, if we're talking about the derivative operator, if we start out with f of x going in, and then we take the derivative, and let me actually denote that d dx. So if we take the derivative, then we get f prime of x. So for example, if our function going in is x squared, when we do the derivative d dx, okay, let me write y equals x squared, then the derivative is y prime equals 2x. So for the first function, the independent variable is x, the dependent variable is y, and then when we take the derivative, the independent variable is still x, the dependent variable is y prime now. Okay, so when we're dealing with an operator, function in, function out, and both functions have the same independent variable. So now let's go to the idea of a transform. So a transform is like an operator. It takes in a function and gives a function out. So again, function in, function out. But what makes a transform different than an operator is that the function going in and the function going out have different independent variables. So the transform that we're interested in right now, of course, is, as I've mentioned, the Laplace transform. So we just want to think of it for now as a black box. We'll learn later what goes on inside the box. The name of that box is going to be a script capital L. And what we're going to do is put into it a function of time. So there'll be some f of t that goes in. So the independent variable is t. And the symbolism we're going to use for what comes out is capital F. So little f will become capital F, and the independent variable would become s. Okay, so that's the result when we do the Laplace transform on little f of t. Okay, so this is the notation we use, and this is how we can think of the Laplace transform. It's a black box, and it takes functions of t and turns them into functions of s. All right, so that's all you know about it right now, is that it takes a function in, function of t, gives a function of s out. Now we can describe it to some extent by giving a table. So Laplace transform . All right, so let's give a table for Laplace transform. So I'll put on the left side f of t, that's the inputs, And on the right side, I'll put f of s, which are the outputs. Okay? And so the first thing we want to think of is if it turns out if f of t, little f of t is 0, then capital F of s is 0. So that's not really very interesting. But the first thing that we are interested in is if little f of t is just the constant function 1, then f of s is 1 over s. If little f of t is just t, then capital F of s is 1 over s squared. And if little f of t is t squared, then we get 2 over s cubed. And we could go on and give other powers of t, but let's move on. If we have an exponential e to the at, then the Laplace transform is 1 over s minus a. If we have our little f of t is sine of at, then the Laplace transform is a over s squared plus a squared. And if our little f of t is cosine of at, then the Laplace transform is s over s squared plus a squared. So that's a table that tells us the Laplace transforms of some functions. So let's say, for example, I wanted to take the Laplace transform of e to the minus 3t. Well, all I have to do is look at the table, and the e to the minus 3t, this is our f of t, little f of t. Okay, and so I can see that when little f of t is e to the at, the transform is 1 over s minus the a. So in this case, the Laplace transform will be 1 over s minus, a is negative 3 in this case, negative 3. So that then, of course, is 1 over s plus a. If I wanted the Laplace transform of, say, well, I mean, this is pretty straightforward. The Laplace transform of t squared, looking at our table, is just straight away 2 over s to the third. And the Laplace transform of, say, sine of 2t, looking at the table, that's going to be, the value of a is 2, so that's 2 over s squared plus 2 squared, which is 4. So those are some Laplace transforms that we can get by using the table. So that's pretty limiting to use just the table itself, but the Laplace transform, the good news is that the Laplace transform is linear. So for instance, if I do the Laplace transform of f of t plus g of t, little f and little g, that's equal to the Laplace transform of f of t plus the Laplace transform of little g of t, and the Laplace transform of f of t, little f of t, is capital F of s, and the Laplace transform of little g of t is capital G of s. So if I want to do the Laplace transform of the sum of two things, that's equal to the sum of the individual Laplace transforms. Similarly, if I have Laplace transform of a constant times f of t, that's equal to the constant times the Laplace transform of f of t. So in other words, the Laplace transform can pass through the constant, and so that would be c capital F of s. So let's bring our table back in and use this, see how we can use this linearity property. So again, f of t, let me just put a couple entries. If f of t, we got f of t and f of s. And let's start, well, actually, I'm going to put most of them back in. So we have 1 t squared e to the t. And let's put in cosine of at. Okay, so cosine at. We'll leave the sign out. This was 1 over s squared, 2 over s cubed. And the e to the at was 1 over s minus a. And the Laplace transform of cosine at, remember, was s over s squared plus a squared. So let's suppose that I knew that little f of t was something like 3t squared minus 7e to the 2t plus 4 cosine of, say, negative 3t. And I want to know what the Laplace transform capital F of s is. Okay, so to find the Laplace transform of capital F of s, I simply apply the transform to little f of t. So I've got the Laplace transform applied to little f of t is equal to the Laplace transform applied to the entire function we're working with, which was 3t squared minus 7e to the 2t plus 4 cosine of negative 3t. But because the Laplace transform is linear, I can first distribute it to each term in here. So we've got the Laplace transform of 3t squared minus, or let's put plus, the Laplace transform of negative 7e to the 2t plus the Laplace transform of 4 cosine of negative 3t. And now that's one of our linearity properties. The other one is that the Laplace transform can pass across the constants. So we have 3 times the Laplace transform of t squared minus 7 times the Laplace transform of e to the 2t plus 4 times the Laplace transform of cosine negative 3t. And now we can use the table to help us out. So we see from the table that the Laplace transform of t squared is 2 over s cubed. So we have 3 times 2 over s cubed minus 7. Then the Laplace transform of e to the 2t will be 1 over s minus 2. And then we have plus 4. And the Laplace transform of cosine of negative 3t will be s over s squared plus a squared. The a is negative 3, so negative 3 squared is positive 9. And then we can just tidy this up a little bit and we're done. So 3 times 2 is 6. We've got 6 over s cubed minus 7 over s minus 2 plus 4s over s squared plus 9. Okay, so that's a brief introduction to what the Laplace transform is. Now, of course, this table that we've drawn, where those entries come from is a total mystery to you right now. And that's okay. We can just work with that for now, and then we'll see later where those transforms come from. We'll actually understand the inner workings of the Laplace transform machine. In the next video, what we're going to do is we're going to see that we want to also have another machine called the inverse Laplace transform that gets us from capital F of s back to little f of t. So we'll tackle that in the next video.